What is the output of this circuit given two inputs V in and the 10 volt DC input that are shown in this circuit and two ideal op amps? There is a short and quick way of computing this, but that requires observing an important factor happening for the second op amp here. To get to that, let's first start with the virtual short that is valid for the two op amps that are shown here. Virtual short indicate that if op amp are properly biased, so they have the proper positive and negative supply voltage and they are not saturated, basically negative feedback is dominant, which is the case in these circuits, and at the same time they are ideal and they are in linear region. So with op amps in linear region of operation, I can say virtual short is valid for both op amp, which means that the voltage at input positive terminal should be equal to the voltage at negative terminal. For the first op amp here, you can see the positive terminal is zeroed, so negative terminal, because of virtual short, is zeroed. Now, for the second op amp, you can see that from V out, there is a simple voltage division across 40 and 20K. It's easy to observe that the voltage at negative input terminal of the second op amp is just as simple as saying for the second op amp, I can say the voltage at negative terminal is simply V out times 20K divided by series of 20 and 40. So 20 divided by 20 plus 40 times V out, which means we get to V negative for the second op amp equal to V out over 3. Okay, so let's keep this. So it means this node has a voltage of V out over 3. And because of virtual short, it means that at positive input terminal, we also have V out over 3. Okay, so with that in mind, now we can write a simple KCL at negative input terminal of the first op amp. So the current that is coming from V in, IN, and the current that is coming from 10 volt IDC, that's the DC supply, should be equal to the current that goes out this way and this way. So we have two currents that are coming in, IN and IDC, and you have two currents that are going out. Remember that because op amp is ideal, input impedance of op amp is infinite, so no current can flow through terminal of op amp. So this current is zero. So therefore, writing a KCL at, say, this node, which is at node X, will give me this outcome. For I in, I'm going to write V in and minus voltage at node X is 0 because of the virtual short for the first op amp. So V in divided by just 5K. Okay, plus we have IDC, which is 10 volt minus 0, which is 10 volt divided by 20K. So 10 divided by 20K equal to, now we have 0, which is the voltage at at X, minus V over 3 divided by 20K. That's the current going outward through the 20K. So it would be negative V out over 3 divided by 20K. And finally, we have this current that goes outward from node X toward 40K toward the output. So 0 minus V out divided by 40K. So I need to just make sure I'm not missing something. 0 minus V out, so you can say minus V out divided by 40K. Okay, we found the equation that we needed. We utilized this information here by having this voltage at V out over 3, and then we have one equation that relates V out to say the combination of the two input voltages V in and 10. So let's expand on it quickly. So what I'm going to get is multiplying both sides, say by, let's say we multiply both sides by, actually we can do a simplification, but nonetheless we can multiply both sides by 60K, and as a result, if we do that, 60 divided by 5K, we get 12 V in plus 30 is equal to minus V out and then we have minus 60k divided by 40k give us 1.5 V out. So we get minus 2.5 V out. Okay, so we have minus 2.5 V out equal to 30 plus 12 V in. So in summary, what we're going to get is V out is simply 12 divided by negative 2.5. So it becomes negative 12 divided by 2.5 V in, and we get negative 30 divided by 2.5 for the DC contribution. Now we can compute this, of course, if we want, and the result will be the outcome for V out as defined by V in by and also the DC. There is a faster way to compute this if we want. The faster way would be the second method, faster method. So second method, which is the faster method here of computing this outcome. So faster method is this way. All right, so we observed that here we have V out that is connecting to 40K, and then we have V out over 3. So effectively, what is happening is we have a circuit that 40K connected on one side to 0 and the other side to V out. And then we have the 20K that is connected on one side to 0, and then we have on the other side V out over 3. So if we want to sort of emulate this circuit or have an equivalence for it, we can show the circuit like this based on one op amp effectively. We can say we have the first op amp that is shown here, negative plus connected to ground, and then we have on top, what we can do is instead of 20K, I'm going to show we have as if 60K. So let me write it below. So as if we have 60K 3 times 20K, but as if we are at V out. And what's going to happen is now I have the usual 40K that is connected to V out on the top. And also here we have the 20K that connects to DC of 10 volt, and we have 5K that is connected to V in. Okay, the reason that I'm saying this is faster because as you can see, this is now a simple op-amp circuit that is in inverting mode, so inverting amplifier. As we can just write an overall resistor here. So for the combination of these two resistors, we have two resistors in parallel, so 40K and 60K in parallel. What I can do is I can just write them instead of them, write them 40K parallel with 60K, and that will be equal to 40 times 60 divided by 100, which is 24K. So instead of 40 and 60, I can write 24K. Now I have two input voltages that are applied to this non-inverting amplifier. We know that for each of them, we can simply say there's a gain of negative feedback resistor, which is 24K, divided by the resistor that is connected to that voltage. So effectively, I can just quickly say V out is minus 24K divided by, on one side, we have 5K times V in, and minus, again, it's an inverting amplifier. So minus, we have 24K divided by the 20K that we have for, sorry, this one is not, this one is, I'm trying to just make sure I'm not missing something. Yes, it's 20K. So it's 20K and then times 10 volts. Okay, so If we use this, you can see that this first one is exactly what you have here. So effectively, if you simplify this, it become negative 4.8. I think so. It become negative 4.8 VN. And then over here, we have 24K divided by 2, which become 2K, which become minus 12 volt. The same thing as on top. Over here, if you simplify, you can exactly see that this become exactly as you have here. Negative 12 over 2.5 becomes negative 4.8 V in. And for this one, this 30 divided by 2.5 also give you minus 12. So we have a match. So as you can see, the second method was a faster method, but it needed to rely on the knowledge of knowing what is the formula for the gain of the inverting amplifier. That in general, for an inverting amplifier in this form, so negative feedback, positive and positive terminal grounded, let's say as a reference, and you have RF and then V out, and you have R in or R1 and voltage V in. In this case, the gain or V out over V in is just simply negative RF over R1. So I use that information to get to this outcome basically. So the second method relied on that. I hope that this is helpful.